This lesson looks at the rest of 6.3, which is the applications of parametric equations in the real world. So first we're going to look at the type of problem we're going to see. We're not going to actually do this one, but example 8 from the book says a distress flare is shot straight up from a ship's bridge 75 feet above the water with an initial velocity of 76 feet per second. Graph the flare's height against time, give the height of the flare above the water at each time, and simulate the flare's motion for each length of time. So you can see that this gives us the equation of projectile motion, which we used before. Now, that equation allows us to find the height of the equation. Having said that, if we can use parametrics, we should also be able to find the horizontal distance, the x equation, in terms of t as well. And that's kind of what we're looking at today. Some other follow-up questions to problems like this will be how long is in the air and what is the max height. So we've done a little bit of that already, and we'll talk about that as well. Before we start, we do have to get some key things down that we'll need. And so we're talking about parametric equations for projectile motion problems. First, we always need to remember that vectors in component form look like this. We've already talked about this a few times, but it is the magnitude times cosine theta. But if we're talking about projectile motion, it would be the initial velocity is the magnitude times cosine theta. And then the initial velocity times sine of theta. Okay, so that's the vector and component form for these types of problems. If we're talking and like I said, what's going to be different is we're going to have a second equation for x. And x is our horizontal axis, so this will give us the horizontal. That makes it 0 cosine theta times t. So this one will always give us the horizontal distance because x is horizontal. And then y is our good old-fashioned parametric equation. Squared plus, in this case, it's b sub 0 sine theta times t plus the initial height. Okay? Now just a quick thing. If the problem is in meters, we would use negative 4.9 here. The negative 16 is when it's in feet. There is a problem that asks, puts it in meters, so there will be one you need to do negative 4.9 for. Okay, so again, we've already talked about this before, but just a quick summary of what these things mean. The v sub 0 is the initial velocity. Theta is the math angle, which will be in the problem, that the object is released at. The reason I say math angle is because in past we've had different types of problems that have bearing and stuff. These will actually give you the math angle. H sub 0 is the initial height. We already said that the x equation is the horizontal distance. And then y is the vertical distance. Which means you're finding the height. So these are the equations that we need to know, and once we have them, we're able to apply them to real-world problems. And we're just going to do one example of those, and then you're going to be set free to kind of work on some examples together. So this comes from the book. It's book example number 9 if you want to look back at it. But it says, Kevin hits a baseball at 3 feet above the ground with an initial speed of 150 feet per second at an angle of 18 degrees with the horizontal. Will the ball clear a 20-foot wall that is 400 feet away? So you can see the real-world application of this in terms of we're really deciding will he hit a home run. So the question is, will the ball clear the 20-foot wall? That's not the question I can necessarily answer first. So I'm talking about both height and horizontal distance. So I need both of the equations. So I actually start with my x equation. So these are the types of questions we can ask, but I'm just going to do some work over here. So my x equation, which is the horizontal distance, is the initial velocity, so 150. X is always cosine. And theta is 18 degrees, the horizontal. Okay? And it's times t. Okay? That's my equation for x. Now, I need to figure out how long it takes to get to the wall, because this equation is then going to allow me to find the height at that time. So my height equation, though, will be y equals, and then it's negative 16 because we're talking about feet, t squared plus initial velocity times sine of theta, so 18 degrees times t, plus the initial height. The ball is hit from 3 feet above ground, so it's plus 3. So those are my two equations. Ultimately, I want to know the height when it reaches the wall. The problem is my height equation, so this is my height equation, only has t's in it, which is time. So I actually first need to find the time that it takes to get to the wall that is 400 feet away. So this is a horizontal distance, so I plug in the 400 for my x equation, and you can see that that just leaves me with t to solve for. In order to solve, I would just divide both sides by 150 cosine 18 degrees, 50 cosine 18 degrees. I type that into my calculator. My calculator gives me 2.8, which means it takes 2.8 seconds to hit the wall. And then I would plug 2.8 in for my t. So the height, 2.8 seconds, is negative 16 times 2.8 squared plus 150 sine 18 times 2.8. Probably put this in parentheses when I type it in, plus 3. I type it all into my calculator, and I get 7.35 feet. So that is the height of the ball. So what this represents is the height of ball after 2.8 seconds, which means it's 400 feet. Now, we said it needs to clear a 20-foot wall, so the answer is no. No, it will not clear the 20-foot wall. This is ultimately my answer for question A. Okay, so now that we answered question A, which is kind of the big picture type question we want to be able to answer with these, we're going to go on to B, C, and D. B and C are actually a review of something we've done before. They say, what is the max height and when does the ball reach its max height? Now, since both of those have the word height in them, I know that I'm going to use the y equation. And then I remember to what we worked on before. If I don't have a graphing calculator, if I can graph it, I could just do that. If I don't have a graphing calculator, I can actually find b, and then I'm going to take that out. So I take negative b, which negative my b is the 150 sine 18 degrees over 2 times a is negative 16. I typed that into my calculator and I got 1.45 seconds. So it takes 1.45 seconds for the ball to reach its max, and then I can take that answer and I can take my height equation, plug that in for t, times 1.45 squared, sine 18, 5. If I plug that into my calculator, that gives the max height, which I ended up getting 36.57 feet. And then the last question, part D, says how far away from the initial hit is it when it reaches? Now, since we know that it reaches its max height when t is 1.45, I plug it. So I get x equals 150 cosine 18 times 1.45. When I type that in, I got 206.85 feet. So that's the horizontal distance to the maximum. So again, the nice thing about parametric equations is it allows us to think about two different dimensions at the same time. Before we were introduced to this, we had projectile motion, which only allowed us to talk about time and height. Now we can talk about horizontal distance as well. Okay, so now that you've seen an example, now you've seen everything from parametrics with these 2 videos. You are ready for all of assignment number 3. It's worksheet B in your packet, numbers 1 through 11. Remember on the last video I said to cross off 6 and 7. I also told you that in class. And then I also want to make sure you change number 5, make it more simple to the one like we did in the last video, x equals 5 cosine t and y equals 5 sine. Okay, so you're doing 1 through 5 with this change, and then 8 through 11. When I come back, or once you finish that assignment, then you should start working on your chapter review for the rest of today and on Friday. Then on Monday, we will continue the review. Thanks.